Hi, and welcome to our introduction on slope. We're going to talk in this video about the concept of slope and talk about some of the intuition that goes behind it. And you hear about slope, or maybe you haven't heard about slope, but whether it's your first time or you've heard about it a bunch of times, we want you to start to think, okay, why are we even learning about this concept? Why does it really even matter? Why do we need to have this concept of slope? Or is this just some math topic that we're throwing at you and we want you to learn it because it's another topic you need to know, right? Well, that's how you might feel. You might feel like all these topics just compound on each other and it's just one thing to learn after the other, but really these things have direct connections to our lives. Slope is a word you would use if you've ever dealt with anything on a mountain or a hill. So let's take it from that angle as to why we might want to think about slope. And there are many ways to think about this. But let's say we have these two mountains right here. And I don't have, well, let's make names for them. Here we have the blue mountain because the snow is a little bit more blue. And on the blue mountain, you might notice something. You might notice that the slope of the mountain is steeper than Yellow Mountain, right? So we have Blue Mountain and we have Yellow Mountain over here, right? And you might notice as a skier or a hiker, or if you've ever gone up or down a hill, that this hill, the blue hill, is steeper. And that's where the concept of slope really starts to come into play. It's a concept that allows us to talk and think about and discuss and compare and analyze the concept of steepness, right? So the blue hill is steeper than the yellow hill, which is less steep. And we could say it that way, we can end it there, but that's not as far as we're going to go. We're going to go much further because slope allows us to have a much more sophisticated conversation about this. I mean, think about it this way. Let's say you're up on the hill right here, right? And you're skiing downhill, right? You start here, and maybe you go, I don't know, let's say that this is 100 feet, and then you stop. You stop because you want to just take in the view, and maybe there's a little ledge right here, so you go down, and then you stop right here. And let's say that's about 100 feet, and you're having a great time, and you're stopping, and you're admiring the view. Well, how would we describe how that compares maybe to your friend who's over on this next mountain over here? Let's just change colors. Maybe they're right here, and you can even see them. You guys are talking across the mountain, and they go skiing too. But this hill's not as difficult, right? And they ride 100 feet, let's say, just like you did, right? So you rode 100 feet and they rode 100 feet, and, well, you want to compare the trips. Well, notice distance is not enough. In fact, distance is not the way we're going to compare this. It turns out if we're both going 100 feet, and that's the only tool that we have to describe what happened, then we're at a loss to compare these two different trips. And that's where slope really comes into play. What slope would do is say, okay, yeah, you went 100 feet here and you went 100 feet there, but how much did your vertical distance change? So when you start here, right, we can think of this almost as like a point, right? We can also think of our point down here. So we have a start location and a finish location. We have 2 points. And really, instead of asking what's the distance between them, we're going to ask, how much did your vertical distance change in comparison to your horizontal distance? And this is forming a right triangle where you find the 2 legs. And over here, you can begin to see that in this triangle, when we look at your vertical change in comparison to your horizontal change, you get a much less dramatic difference. In other words, the slope is not as steep. So we begin to create this mathematics that allows us to describe the difference in both trips here. For example, this trip on the left, right? We know that the mountain's steeper intuitively. Let's put some language to that intuition. This change, right, is our vertical change. We call that our rise. So you want to get used to the phrase that this is your rise versus this over here, which we usually refer to as the run. If you want a better way of describing it, you might describe it as delta y and delta x. Now delta y and delta x, that's saying, delta y is saying how much did your y-axis change, and y is height. Delta x is saying how much did your x-axis change, or your left and right distance, your horizontal difference. It's a ratio. Here, let's say if this was 100 feet, right, and we have this right triangle, we can think of this as like a 3, 4, 5, but it's been scaled up dramatically, where it's been scaled up by 20. So maybe the rise here, right, is 80 feet, right, and the run here is 60 feet. So this right triangle right here tells you that your rise changed by 80 feet and your run changed by 60 feet. So what's the slope of this steep mountain? Well, this is what's interesting here, because if you calculate your slope, slope is the variable m is used for slope because that refers to mountain. Here you have delta y, 80, over delta x, or slope is really a ratio of y over x, which is 8 over 6, right, or 4/3. And that just means if the slope and the rate of change of this mountain is constant, let's assume it pretty much is, even though I didn't draw it that way. If the slope is always changing the same, the mountain was always changing this way, that would mean every 4 feet you drop your delta y, right, your delta x, your horizontal position, changes by 3 feet. In fact, instead of having one large triangle, you could have a bunch of smaller triangles that accomplish the same thing. You could think of this as a smaller scale. What I mean is, like, you can go from this point down about halfway and then over, right, to this point right here and do it again and get to the same location. And these smaller triangles, instead of going 80 and 60, would go 40 and 30, 40 and 30, and you still end up at the same location. In other videos, we'll talk about how to deal with a mountain where the slope is constantly changing. That's a really fun way to really get at calculus and some other wonderful concepts. So in this part of the mountain, right, where let's say the slope is constant, that was the experience you had when you rode this part of the mountain. You dropped 80 feet and went over 60, and that's the slope. Over here, we can almost reverse that. We can say that your drop, your delta y here, your change in your rise is equal to, let's say, 60 feet, but your run is equal, delta x is equal to 80 feet. So that just means that for this less steep mountain, what does that mean? Well, m is equal to what? Slope is equal to the ratio of your change in y over your change in x, how much you're dropping and how much you're going over. And here, delta y over delta x is the reverse, right? Delta y is 60 and delta x is 80. So it's 6 over 8, or 3/4. Now here, you can compare these slopes in this way. The higher the slope, the steeper the line. So here, this is a higher ratio, right? 4 over 3 is higher than 3 over 4. 4/3 is bigger than 3/4. And that tells us that our slope here is steeper. So a higher slope means a steeper result. So 4/3 is greater than 3/4, and that's your slope comparison. That's a mathematical way of saying, hey, the slope the slope on this mountain over here on Blue Mountain is steeper than Yellow Mountain. So that might seem like a big workaround for an obvious kind of concept that, hey, this mountain's steeper. But think about the power of this statement. Think about how we're now able to talk about not just distance, but rate of change. On a graph, we can do all kinds of stuff with this. Like, so here's a little Geogebra app I set up. We have these 2 points. We're going from 0, 1 to 4, 5. The slope is the steepness of this line. So you could say, all right, to get from this point to that point, how far over do I go and how far up do I go? And when you ask that question, you're talking about slope. So the slope of this line is just 1, because your change in y is 1, 2, 3, 4, and your change in x is 1, 2, 3, 4. So here your slope is just 4 over 4, or 1. And we can mess with this if I go like this right here. And we'll talk about the equation in a moment. Here what happens? Well, now I made a steeper line, right? Before it was here, and now it's here, right? And as I drop this down further and further and further, the line gets steeper and steeper and steeper. Now this setup is giving us decimals, but usually you can just think of this in terms of fractions. So here, what's our slope? Well, count. What's your rise to get from this point to this point? Well, we go down 1, 2, 3, 4, 5, and back 1, 2, 3, 4. So it's like -5, -4, that's a positive, right? Negative over negative is a positive, and it's 5 over 4. That would be your slope. Or as they wrote, 1.25. 1.25 and 5 over 4, of course, are equivalent. And as you drag this point down further and further and further, you get steeper and steeper slopes. Like here we have our slope. Let's just count this last one. 1, 2, 3, 4, 5, 6, 7, 8. Down 8 and back 1, 2, 3, 4. So 8 over 4, that's our slope, our change in our rise, and our change in our run, that's 2. And notice this equation has the 2 there, and we'll talk about that because this is a pretty standard way of writing the equations of lines that includes your slope and your y-intercept. But I do want to talk for a moment about this problem because it does, I don't know if it seems this way to you, but it does seem kind of tedious to have to count for the slope every single time. Imagine how impractical it would be if our points were thousands of places apart. So let me just grab that and we're going to work with this problem and look at a faster way of doing it. Alright, so we've got this triangle here and this equation. We want to find the slope. Well, think about it, right? If we're going from this point to this one, how can we avoid counting the vertical distance here? That's our change in y. How can we avoid doing that? Take a moment and think about that. Think about the points. We have 4, 5, and 0, -3. Well, if I'm looking at the vertical change, I'm looking at the y values because that refers to how high we are. And what I would just do is subtract, right? 5 minus what? Well, the y value here is -3. What's 5 minus -3? That's just 8. And that means delta y, or a change in y, is 8. And here we can do the same for x. I know we can count here, but again, we want to use a stronger idea to apply some kind of strategy to a much bigger scale, right? So we can solve any problem. And what I would do here, same idea. I would just subtract because we have 4 and 0. So that means, what could we do? Well, that means we can do 4 minus 0, and that's our delta x, right? 4 minus 0, which is just 4. So our slope is, our m value is 8 over 4, or 2. So this kind of brings up our formula for slope, and this is often what you see, right? Slope, they might tell you, is equal to delta y over delta x. Change in y over change in x. And to find your delta y, well, if you have 2 points, and they might call them x1 and y1, that's my comma there, and x2, y2. Don't be intimidated by these little 2's or 1's. That's just a placeholder. It's saying x1 and y1 are the x and y values of your first point, and x2 and y2 are the x and y values of your second point. What did we do here? Well, let's say we call this point our second point. So this could be our x2 and our y2. And we'll see in a moment if we could reverse that as well. And this will be our x1 and our y1. So we subtracted, didn't we? We just subtracted the 2 y values. So our formula is going to be y2 minus y1. Subtract the y values of the points, right? That's what we did right here. That'll tell you your delta y. And then what did we do? Then we subtracted our x values. It gave us our delta x. And since slope is delta y over delta x, fix this color, that means that delta x must equal the difference of the x values, right? x2 minus x1. And that's how we find slope. And the wonderful thing, and we'll try this in a moment, is that you just pick 2 points and subtract the y values over the x values, and that tells you your slope. So 2 questions we often get on this is, could we reverse that? Could we have made this point down here x2, y2, and this point x1, y1? That answer, let's find it out. Let's not just tell it. Let's not just say it. That would kind of ruin it. So let's reverse everything and see if the slope is the same. So now we're taking -3 minus 5, right? We're reversing the y values over the x values, 0 minus 4. What's going to happen? Well, -3 minus 5 is -8, and 0 minus 4 is what? -4. Look at this. Now we have -8 over -4, and that's positive 2, right? Because it's a negative divided by a negative, and that's the same slope that we got before. So, not to memorize this, but you can test the hypothesis. It turns out that you can reverse the order of the points and you'll still get the same slope. Another question we get is, could I have picked different points? Well, let's just look at the geometry of this again. If I used to travel down here and down and over again, the same amount, or the same rate, the same slope, it looks like to me that what's happening? Well, it looks that whether or not we do this big jump, the big triangle, or these two smaller ones, it looks like we follow the same line. But let's test it algebraically. What's this point right here? Well, it's 1, 2, and up 1, so it's 2, 1. If you chose this point right here and compared it to, let's say, this point up here, and calculated slope, will we still get 2? Let's try it. So now m is going to equal what? Well, 5 minus 1, right, over 4 minus 2. And that's just 4 over 2, and that's equal to 2. And you might think about the shapes here again. This is a smaller version of the large triangle. It's proportional. It's 2 this way and 4 this way. The larger triangle was 8 by 4. All the triangles you draw from any 2 points will form similar triangles. You have this wonderful flexibility where you can pick any 2 points, connect them, right? Or even just subtract the y and x values and you'll find the slope. Now, let's just tie this up quickly in the end here, because often you're asked to connect the slope to the equations of lines. And just to gain some basic instinct, look at the structure of this equation. Notice that the slope is right here next to the x value. And wherever you drag these 2 points, right, you get a new slope, but it looks like to me that the slope is always right next to the x value. And there's this other number right here. Here it's negative 1. Negative 1 I notice is on the graph. In fact, it's right here on this point on the y-axis. Watch what happens to this number as I move my line up or down. So as I move it up, the line changes, the equation changes, and the line changes, but this point is going up. When I stop at 0, it's gone because it's 0. When I go up to 1, that number becomes 1. When I go up to 2, it becomes 2. When I drop down to negative 3, it becomes negative 3. That tells me that this point on the y-axis, which we call the y-intercept, is always going to be this number in the equation, and this number here is always going to be the slope. That's a very basic connection to make. And we're just making the observation. We're not even asking why this happens yet. But, let me just grab this. Let's go to one last spot here, because this is one last thing we want to cover here. Alright, let me just get this. Okay, so here, right, we have this basic idea that there's an equation that connects to a line. And we want to realize that the number next to the x value can be observed to be the m value or the slope. And this value right here, right, can be observed to be what we call the b value or the y-intercept. That's the point that intersects this, the y-axis, right? So there's this wonderful connection that if you have a line, if I gave you a picture, or if I gave you 2 points, if you find the slope and it happens to be 2, you know that you can write your equation for your line like this, where y equals m times x, or slope times x, plus b. So if I gave you these 2 points, 4, 5, and 0, negative 3, what you would do is subtract them just like we did, and you get the slope, which is 2. And you start to write the equation. Y equals 2x, and then it's going to be plus a negative 3, or like they wrote minus 3. Because what you want to realize is that you can find the y-intercept when your x value is equal to 0. Sometimes they won't give you the y-intercept. They might give you a second point right here. 2, 1 it was, I believe. Yep. Over 2 up 1. In that case, you find the slope, you get 2. And you'd be stuck in this spot right here, where y equals 2x plus b, because you don't know it, let's say. Well, one way to find the b value, and this is the beautiful connection here between the line and the equation, is that you can plug this point. In fact, you can plug any point into your equation, and then what will happen is you can solve for the missing y-intercept. And the way you plug a point into an equation like this is the following. The first number 2 is your x value, and the second number 1 is your y value. Because points, remember, are x and y. So this equation is a collection of points where the x and y values are equal and the slope is when the x and y values balance the equation. They're not equal, sorry, but they balance the equation when the slope is 2 and the y-intercept is -3. Now you don't know that yet, you're going to plug that in. So y is equal to 1, and that equals 2 times x, and x is 2, so it's slope times 2 plus b. So it's b plus 4 equals 1. Subtract 4 from both sides, or just realize that b is equal to -3, right? Because -3 plus 4 is 1. And in that way, you could find your b value and then have the equation for your line. Now, that's a lot to digest right there, but we really wanted to get you started with slope intuition, where you can just find this idea of slope and frame it in a way that really makes sense to you and realize the power of it. It allows us to describe just how steep these lines really are. All right, thanks a lot.